Okay, we're at 16.7, energy in a capacitor. Let's go to the PowerPoint. Capacitors are I mean, we'll see that they have many applications, but one of their applications is storing energy. If you have a little uh, portable camera and it has a built-in flash unit, a lot of times once you fire a flash photograph, there's a little, at least on mine, there's a little indicator light that kind of flashes red until there's been enough charge to it's gathered enough charge to light the flash again, because you can't just rapid fire the flash off. It needs to charge. The capacitor needs to charge, so it's capable of storing energy, and we're going to discuss that. We can see that if you recall from a previous chapter, for uh, uh, in that case, it was a variable force. For a variable force, the uh, energy was area under the curve. Well, here the energy in the capacitor, since we have a varying voltage, you vary the voltage, the charge is related to the voltage. The work is equal to Q minus Q times VB minus VA, the potential difference, the electric potential. And so the work is equal to delta V times delta Q. Um, Delta V is equal to Q over divided by C. So the work is equal to 1/2 Q delta V. The work is equal to 1/2 Q delta V. It's that area under the curve. So W is equal to 1/2 QV. Q is equal to C delta V. So the potential energy can be expressed as equal to 1/2 Q delta V, or it can be, if you substitute uh, C delta V where the Q is, you get 1/2 C delta V squared, or if you substitute delta V equals Q over C, then you get Q squared, PE, the potential, the energy in the capacitor is Q squared over 2C. It's 1/2 Q squared over 1/2 Q squared over C. And let's look at an example. Let's say we have a 5 microfarad capacitor and 120 volts. So the energy stored is 1/2 C delta V squared is equal to 1/2 5 times 10 to the minus 6 farads times 120 volts squared. And you end up with 3.6 times 10 to the minus 2 joules. That's the energy stored in the capacitor. Okay, and here's another application of energy stored in the capacitor, and that would be in these uh, uh, like a defibrillator. Uh, they use these defibrillators, and the battery in it can charge up a capacitor large enough that when it needs to be applied to a patient using the paddles, it can discharge a large amount of energy to get the heart regulated again. Um, the stored electrical energy is released through the heart by conducting electrodes called paddles placed on both sides of the victim's chest. The paramedics must wait between applications of the electrical energy because of the time it takes the capacitor to become fully charged. It's just like waiting for your camera flash to charge up. Um, and some capacitors can can pack a punch, even enough to cause death, because it's the amount of current, which relates to charge. It's the amount of current that is dangerous. You can have a high voltage source that has very capability of very little current. It'll sting like crazy and cause your muscles to contract, but it won't kill you. I'm not recommending that you try it, but if you have a lot of current capability, it is very dangerous, and it can kill you. Okay, now we're going to stop there, and we're going to go on with capacitors with dielectrics, and how that changes things.